Now good morning everyone. So continuing with the previous lecture of finding the Laplace transform and inverse Laplace transform, we will continue here. We will discuss only the basic details since the Laplace transform you have done in mathematics portion also. So let us consider a function. We have to find the Laplace transform of that particular function. So while finding the Laplace transform, multiply that function with e minus st from 0 to infinity, and after calculating this we finally get the answer as e divided by s plus a. Now let us consider another example of the Laplace transform. Let us suppose that we have a function ft equals to 1 and we want to find the Laplace transform of that function. So to find the Laplace transform of that very function, we have to write the equation like that, that is from 0 to infinity e minus st dt, which is equals to 1 by minus 1 by s e minus st 0 to infinity, which is equals to 1 divided by s. However, such type of integral is called the improper integral, and to find the solve this improper integral, you have to do like that: e minus st ft dt, which is equals to limit of t tends to infinity 0 to t e minus st ft dt. So come to one more example, that its answer is 1 divided by s. Now come to one more example. Now let us suppose that you have to find the Laplace transform of e raised to power a t. So we have to find the Laplace transform of e raised to power a t. So continuing like in the previous case, Laplace of e a t is equals to 0 to infinity e minus st e a t dt, which is equals to 1 divided by a minus s e minus s minus a into t limit from 0 to infinity, and for s minus a equals to s minus a greater than 0, the Laplace transform e a t is equals to 1 divided by s minus a. So in this way we have to find the Laplace transform of any function. Now instead of finding the Laplace transform of the function like that, there are certain things that has already been there are Laplace transform of certain functions that are already available. Like you see impulse response, it is 1. For unit step it is 1 by s, and then t ut equal to 1 by s square, and for t and ut the formula is n factorial divided by s plus s raised to power n plus 1. So these are certain this is a Laplace transform table which is used to find the Laplace transform of functions. Also, to find the Laplace transform, we have to use the Laplace transform theorems. Like you have the linearity theorem, that is if two functions are there, if we want to find the Laplace transform of two functions, we can simply add the if we want to find the Laplace transform of a total function, you can simply add that function, that is linearity theorem. Then we have the frequency shift theorem, that is the function is shift by a. In this way, there are different theorems that we can use to solve the problems of the Laplace transform. Like we have the differentiation, it can be represented by sfs minus this function. Then we have integration, it can be represented by fs divided by s. Then we have two theorems which are generally used to find the response at t equal to infinity and t equal to 0. For t equal to infinity, we can use the final value theorem. In case of final value theorem, this function can be represented by as fs and then limit of s tends to 0. We can get the response at t equals to infinity. And second is the initial value theorem. In case of initial value theorem, we can find the Laplace transform of the function and represent it as fs and then limit of s tends to infinity. Then we can find the response at f equal to, that is find the response at at t equals to 0. So also one point is there that this function must be continuous, or it has a step discontinuity, like it is a piecewise continuous, that we have discussed in the previous lecture also, that this function should be piecewise continuous function. Then we can be able to find the Laplace transform of this function. Now consider example in which we have to use this table 2.1 and table 2.2 to find the inverse Laplace transform. And now let us suppose that we have a function, let us suppose that we take a function f1s is equals to 1 by s plus 3 square. Now we have to find the inverse Laplace transform of this. Now in this case we have to use the two things, that is, one is tut equals to 1 by s square, we have to use this one, and second one we have to use this frequency shift theorem to find the value of this. Now you will see ft can be represented by, as we have already discussed, that ft, we can represent the ft as u as t u t. So we have to use the frequency shift theorem and the Laplace transform of this t u t. Now we already know that the Laplace that is for 1 by s, the Laplace that is let us suppose that we have function fs equals to 1 by s square. Now the inverse Laplace transform of this is t ut. It is t ut. So inverse Laplace transform of fs plus a is equals to 1 divided by, that is inverse Laplace transform of fs plus a, that is 1 divided by s plus a whole square is given by e minus a t t ut. We have used both these things in that. First this one and second is the frequency shift theorem, and finally we are getting the value as, since in this case a is 3, so So finally we will get e minus 3t t u t. In this way we have to use the combination of different theorems and these values given, so to find the exact value of any, that is Laplace transform of any function and inverse Laplace transform of any function. Now before discussing this partial fraction, we can discuss about the order and degree of any differential equation. Now let us consider a differential equation. Let us suppose that we have a differential equation d square y divided by ds2 3 plus dy by dx plus y is equals to 4 x square. Now in this case the order of the differential equation is 2. This is the order of the differential equation, and degree of this differential equation is 3. So the order is actually the highest derivative. So order is the highest derivative. In this case the highest derivative is 2, so in this case the order is 2. Now let us consider another example. Let us suppose that we have dy by dt plus y square is equals to 5x. In this case we can say that order is 1, since the highest derivative in this case is 1 only. Now let us take another example, that is x cube plus dy by dx plus y is equals to ex. In this case we will see that it has what is the order of differential equation? So in this case the order of the differential equation is 3. Now take an example in which let us suppose that it has the exponent of 2, that is dy by dt with the power of 2, then we can say that its degree is 2. So what is the, so we can define the degree as the exponent of highest derivative, that is it is the exponent of highest derivative. So this equation has the, that is it has the exponent 2, so it is the first order and second degree ordinary differential equation, that is first order, that is dy by dt only, and second degree because it has exponent 2, that is the highest derivative has the exponent 2, so second degree ordinary differential equation, that is its degree is second. Now let us take the case of this. In this case we can see that order is 3 and degree in this case is 1. Now let us take another example. Let us suppose that we have this system. We take this system, that is plus dy by dt. Now see this differential equation, as you can see, the order of this differential equation is 3 and degree of this differential equation is only 1, because the highest derivative has the degree 1. Now let us suppose that we have a differential equation in which this dq y by dx cube and dy by dx, and let us suppose that this dy by d this has exponent 2. So this type of equation is third order and first degree ordinary differential equation. That is, this is third order and first degree ordinary differential equation. Since it has the exponent 2, still its degree is only 1, because the highest derivative is taken into consideration. Now come to the partial fractions. So a partial fraction is actually used to find the inverse Laplace transform. So in case of partial fractions, what we do, let us suppose that we have one function that is a Laplace in S domain, s square plus 1. Now to find the inverse transform of this type of expression, let it be s square minus 1. S square minus 1. Now to find the inverse of this type of expression, we can express this function as the sum of fractions with simpler factor in the denominator. That is, we can work on the denominator and find the simple factor in the denominator and find the inverse Laplace transform in this case. Now let us consider a function. Let us consider a function fs. Now let us suppose that fs is represented by this ns. Ns is the numerator and ds is the denominator. Now if the order of ns is less than the order of ds, that is, the order of ns is less than the order of ds, then partial fraction expansion is possible. That is, if order of ns is less than the order of ds, that is, the order of numerator is less than the order of denominator, then the partial fraction expansion is possible. Now second case, if order of numerator is greater than or equals to the order of denominator, then what we do, we divide ns by ds, that is, we divide this ns by ds successively until the so we divide this ns by ds until we get, that is, order of the ns is less than the order of ds. That is first equation. So we will explain it with some example. Now let us take a function, this one f1s. Since we know that a numerator has order greater than this denominator, so divide it and it can be represented by this. and now we have three distinct terms, s plus 1 and this third one. Now what we do in the partial fraction expansion, we will represent this term. We consider this fs and we expand this into the sum of terms and then find the this inverse Laplace transform in this case. As we know that this inverse Laplace transform of this one is this delta t, and the inverse Laplace transform of s is represented by, that is, Laplace inverse Sn is equals to delta n into t. In this case we have s the power of n, that is n is equals to 1 in this case, so we will get d delta t by dt. So directly we can use the linearity property and the table for finding the value of the inverse Laplace transform. Now to find the inverse Laplace transform of this term we take as a reference, and then we can see the different cases which arises out of that. Like let us suppose that if the roots of fs are real and distinct, that in this case there are some cases. First case is if the roots of the denominator are real and distinct. Second, if the roots of denominator are real and repeated roots, that is s plus 2 raised to power 2. And third case is that if the roots of denominator are complex or imaginary, which arises out of that when we solve this quadratic equation. Now we will take all these cases into consideration and explain, I will explain that how all these cases are solved by this partial fraction expansion to find the inverse Laplace transform. Now take the case 1 in which the roots are real and distinct. In this case, let us suppose that this is the function. We can represent our function like that: k1 divided by s plus 1 plus k2 divided by s plus 2, and we have to find the values of k1 and k2. To find the value of k1 and k2, first we multiply this function by this s plus 1, that is, we multiply this whole function by s plus 1. When we multiply it, then in that very case we are only left with s plus 2 and k1. So we multiply this function with this, and also in this case s approaches minus 1. Okay, first we multiply it with s plus 1, then we use s as equals to minus 1, so it will give the value of k1. Similarly, in the second case we multiply this with s plus 2 whole equation by s plus 2, and in the second case s approaches minus 2 to get the value of k2. So in this way we can get the value of k1 and k2. So finally what we are getting after using this, we get the value of k1 as 2 and k2 as minus 2. So finally we are getting k1 as 2 and k2 is as minus 2. So we got the value of k1 and k2. We express this function with the partial fraction in this way, that is 2 divided by s plus 1 plus this minus 2 divided by s plus 2. Now we used the already given in the table some of the results to find the value of this. So for finding the inverse Laplace transform of 2 divided by s plus 1, it is given by 2 into e minus t, and second one it is given by minus 2 e minus t ut. So in this way we proceed to find the value of this, to find the inverse Laplace transform by the partial fraction expansion. It can be explained by this general term. Let us suppose that we have one function fs and the numerator and denominator is represented by this. Let us suppose that numerator ns and denominator is like that. So we represent the whole of the function in that term, that is k1 divided by s plus p1 plus k2 divided by s plus p2 in this way, and after that we multiply this term like I explained in the previous example. We multiply the first term and then allow the first term to approach this value, that is we use this first term and use this first term as s equals to minus pm, that is we use s equals to minus pm, and finally we will get the value of the km. In this way we can find all the values of k in this way, and we can represent any this function in these terms by the partial fraction expansion. Now let us take an example that we have to find the Laplace transform of this. We have to solve the value of yt if all the initial condition 0 by using the Laplace transform. First of all, this is the differential equation, and now first how we proceed. First of all, we represent that differential equation in the s domain. So this d square y by dt square, it can be represented by s square ys plus 12s ys plus 32y, and for a unit step function ys, and for a unit step function we will get 32 by s, since the Laplace transform of this is 1 by s. So we take the y out of these, we get the y, and finally we get the equation like that. Now this, in this equation the terms are actually these are real and distinct. So what we have learned previously we use in that, that is we express this in the form of k1, k2 and k3, and we have to now find out the value of k1, k2 and k3. To find the value of k1, k2, k3, we first multiply this term, multiply the first term with the whole of this like we have done previously, and then find the value of k1. Then we multiplied this s plus 4 to relieve this s plus 4 out of the whole of the equation, and then proceeds s equals to minus 4 put in that, that is s equals to minus 4, that is done in this case, and find the value of k2. Similarly we can multiply this s plus 8 with the whole of the term, and after that we proceed s equal to minus 8 and we get 1, and in this way we get the value of k1, k2 and k3 and the whole of the value of the ys. So and after that we take this s domain into time domain by using the inverse Laplace transform. As we know that the inverse of this is 1, and then we have s plus 4, that is 2e minus 4t, and at is equal to e minus at ut. So finally we are getting this equation like that. So what we do, we take this time domain, equation in time domain, we convert it into s domain. How to solve this equation in the Laplace transform? We take the time equation in the time domain, then convert it into s domain, and then solve it for y, and after that we take the inverse Laplace and we convert it again into this time domain. Now let us consider where the denominator are real and repeated. So there are different ways to do that. First, in this case, now in the first case what we consider, previous rule cannot be used in that. We represent it like that, k1 divided by s plus 1, and the repeated roots can be represented by s plus 2 square plus s plus 2. We can take the common denominator and then frame these two equations, left hand side and right hand side, and then compare the coefficients of that to find the value. This is the one way to do that. There are different ways to do this. Secondly, we can find the value of the k1 as discussed previously and k3 as discussed previously, and we can use some mathematical manipulations in that to find out the result. So finally, whatever we get the response after this partial Fourier expansion is that. So in this case, the simple way is that you can take the denominator, common denominator, and then since we get the common denominator of the left hand side and the right hand side, and then we can equate that and find the values of all the coefficients in that case. That's easiest way to do that. So if you want to do it with the general formula, then you can use this general formula to find the value of ki. In that very case, the ki equals to 1 divided by I minus 1 factorial di minus 1 f1s divided by dsi minus 1, and s approaches minus p 1 in that very case. So it is also one of the way to solve this equation in which the roots are repeated. Now if the roots are complex and imaginary, there are different ways to do that. The easiest way is that we represent this as k1 divided by s plus p1 and k2s plus k3 divided by s square plus as plus b, and use the identities, that is e j theta plus e minus j theta divided by 2 equal to cos theta, and e j theta plus e minus j theta divided by 2 j equal to sin theta. Now we represent it like this. One of the way is to like that. Second is we represent it like that, that is we divide it into different roots and then use k1, k2 and k3, and as we have found the value of k1, k2 and k3 in the previous case, we will find the value of k1, k2 and k3. That is, for k2 we will approach s equal to minus 1 minus j2, this one. Now we will find the value of this. Finally, we represent this, and finding the inverse Laplace transform of that, and use the identities that we previously discussed, and finally we will get this function in the time domain. So in this way, and the different ways we can find the partial fraction expansion. Now related to the usefulness of this Laplace transform, we will draw a certain diagram. Then after that you will be able to have the concise view that what it is all about. So what is the usefulness of this Laplace transform? That is, we have the suppose that we have the differential equation. We use the Laplace transform to convert it into S domain. And this is in T domain. This is in S domain. Okay. Then after that, it is converted into algebraic equation. That is converted into algebraic equation. Then after that, we will find the solution of that algebraic equation. Then after that, we will use inverse Laplace transform to convert from S domain again to T domain. That is, this is the final solution in the T domain. So finally, we can say that this part is in T domain and this part in the S domain. So we take the differential equation